reasoning that we have with all those applications that we have to do. And that makes it a little bit easier in terms of, you know, your mindset. It's much more like an algebra class where here are the steps that you need to do. There's still going to be some of that integration, detective work where you've got to decide what should I do, but it's not quite as abstract as what we've done. So the first slide is just the basic integration table. We're going to spend a lot of time on these inverse trig ones, these three here. The most important inverse trig one that we're going to see the most, for sure, is the inverse tangent. So that one right there, we are going to see a lot. And inverse sine, we are going to see second most when it comes to the inverse trig functions. So those two, definitely make sure that you familiarize yourselves with those. The trig ones up here, you should already know. The exponential, you should already know. And actually, all these we're going to talk about in the coming days. So we'll get to the point where we should be able to do the inverse trig ones pretty easily. And there's some patterns that we're going to point out that will make it even easier. Natural log, you should have that down by now. That actually does bring up one thing I want to mention about natural log. Let's look right here, because this did show up multiple times on the test. So for example, if we have, this is not the exact one that was on the test. So if we had something like this, that is not in log form. Log form is when the denominator's derivative is exactly the numerator. And what is the derivative of that denominator? 4 cosh, or cosh. So that's not in log form as it is. And there are two ways that we can tweak it a little bit to make it in log form. One of them is to multiply by 1, classic math trick, multiply by 1. Now it's in log form. That denominator's derivative is identically the numerator. And as soon as we have the denominator's derivative identically the numerator, then it's in log form. So then we could say, oh, OK, so this is going to be 1/4 the natural log of the absolute value of the denominator. Plus c. All right, so that is in log form. Another strategy here, let's suppose we wanted to factor. So you could also factor. You could say, oh gosh, that 4 is in the way. The 4 is the problem. If there wasn't the 4 there, then it would be in log form. So we could factor out the 4 from the denominator. And if we factor out the 4 from the denominator, what are we left with in the denominator? Plus 1/4. So if we factor a 4 out of 1, there is no 4 there. So in our mind, what we're doing is saying, OK, well, there's no 4 to pull out there. So what we could do is, again, multiply by 1. We could multiply that by 4/4. So this 4 is going to factor out to the front in the denominator. And then we're left with 1/4. Or you say to yourself, when the 4 gets distributed back, you better end up with the original question. End up with the original denominator when you distribute that 4 back. And so here you have a slightly different answer, but it is also equally correct. So this would be that. OK, so that I saw a couple times. Any questions on either of those approaches? They both make sense? OK, so let's formally talk about these power reduction identities. So we had one example in the first unit that did ask us to integrate a sine squared or a cosine squared. And it was kind of before the book emphasizes this strategy of reducing the power. So let's talk, and we did also see it with the hyperbolics as well. So this is the power reduction for sine. This is the power reduction for cosine. They look super similar, right? They look almost the same. The only thing that's different is that sign right there. And so depending on how you go about memorizing these, you need to come up with some sort of trick to remember which one has the minus and which one has the plus. And it doesn't matter what you come up with, something to remember. Some people will say, oh, for sine, S-I-N, sin is negative. Some people think cosine, co means kind of 2, and you have both the you have both directions of the plus. Coming up with something so you memorize that, because we're going to see this identity a ton. You're going to see it a lot. It'll definitely be on the next exam, probably more than once. So you are going to see these identities quite a bit. So come up with something that works for you. And now, some of you might be interested in the origins of these two identities. Some of you could care less. They come from the double angle identities. So you had a double angle identity for cosine. And so here is the primary double angle for cosine. This is cosine squared minus sine squared. That was the primary double angle for cosine, and then there were two alternatives. So this only really helps you if you know both sine and cosine. And so then you had these two alternatives where you replaced cosine squared with 1 minus sine squared, Pythagorean theorem, or you replace sine squared with 1 minus cosine squared. And so if we replace sine squared with 1 minus cosine squared, the minus will end up with a negative in front of it, and we'll get that. So these two right here, these are where we get those. If you isolate the cosine squared, or you isolate the sine squared with the cosine 2 theta on the other side, that's where those two come from. So they come from the double angle for cosine. All right, so also notice that we call them, in this class we'll call them power reduction identities, because that's our focus. The focus, the thing that allows these to help us, is that the power is going from 2 down to 1, right? The exponent on the cosine here is 1. So the power on sine is going from 2 to a power of 1 on cosine 2 theta. And similarly for the other one. Power is going from 2 to 1. So we're reducing the power. So that's why we call them power reduction identities. And so the cool thing is that they allow us to do the following. So notice that the 2 in the denominator is a constant. So you can think about factoring out that 1/2 straight right out of the gate. So when we replace this, that is what we have. And that, when we look at it, it should jump out at you as something that you can integrate. Right? Now here we have cosine to the 1 power. There is that angle modification, the 2 theta. And what should we be thinking about with that 2 theta? What technique or process are we going to make sure we use? RCR. So this is linear. Anytime we have a linear angle, a linear exponent, a linear quantity inside a square root, we go with the reverse chain rule. So RCR, reverse chain rule. You could use substitution. It's just going to add 3 or 4 steps. Doesn't matter. You could do that. Definitely not the best strategy. You want to be able to do the RCR because it's just a heck of a lot quicker. And that's whenever it's linear. So linear means the exponent is 1. So this is because this is linear. The angle is linear. So we can integrate straight across. We are going to have the integral of 1 is theta. Integral of the cosine function, sine. So we're going to have sine of the same exact angle. The angle doesn't change. But then what does the RCR give us? Divide by 2. Exactly. So that will be our antiderivative. And this is one of those situations where when you look at it, it's partially factored. And that doesn't make sense. If you have a 3-termed expression, you never just pull something out of the first 2 terms. The more correct way to write the final answer here would be to distribute this half so that we're not factoring out of just part of the answer. All right, you all try the second one. Try this cosine one. You should find it should be very similar. See if you can get it. Let's move it over here. Yeah, these are good ones to just practice a couple times because you will see them so many times and you want to try to build it into your psyche that whenever you see a sine squared or a cosine squared, you do the power reduction. Let me know if there's a piece of it you're snagged on. So the power reduces, you double the angle. Okay. That's exactly good observation. Everybody catch that pattern? When the power reduces, the angle doubles, so you should end up with a cosine of 6 theta. So when you, and you don't have to pull the half out right away, but it's kind of in the way. Some other folks will do this. They'll write it as 1/2 plus cosine of 2 theta, so we'll make that a 6 theta when we double it. So you could write it like that. You can factor the half out, but then we had to distribute it anyway. You could do that. Doesn't really matter. Whatever seems most natural to you, you'll get to the same place. So sine is with a negative, cosine is with a positive.
Is that using the RCR?
Not yet. We haven't integrated yet. So as soon as we do the integration, that's when we'll do the RCR. So right now, all we've done is reduce the power before integration. So we have to reduce the power down, and then we can integrate. And when we integrate, that's when we say, oh gosh, we have a linear angle here. So that means we're going to use RCR, because we've got that linear angle. So this is what that will look like. We'll end up with a 1/2 theta. And then integral of cosine. The nice thing is that both these power reductions, you're always integrating cosine. You don't have to like guess. So you're going to have sine of 6 theta. And what will be the denominator? If we have this 2 here, it'll end up being a 12, right? So we'll divide by 6. Dividing by 6, dividing by 2 is dividing by 12. Okay, so here we go. We're on the road to becoming integration ninjas. So substitution, that's our first and primary technique that we know right now. We're going to learn a ton more in this chapter, but right now substitution is the primary technique. If you don't see an immediate antiderivative, then you should say to yourself, oh, is this substitution technique going to work here? Like that's the first thing that you should ask yourself. So when we look at this, we look at the exponent, that's what we should say to ourselves. Now, in this particular case, when we do substitution, so let's do it with substitution, and hopefully you're looking and saying, hey, that's a linear exponent, we could use RCR. And of course, yes, the answer is you definitely should do it that way. But let's just go through the step 4 substitution. Is there anyone that has issues with this? Is that okay with everyone, that differential step? So we have the u differential and the x differential. Now, I don't know how you were taught it in Calc 1, but what a lot of folks will do is say, okay, du dx is the derivative, that's -4. So you're differentiating the u function with respect to x, and then you're multiplying both sides by dx to get that. So you can think of it that way. You can think of it as taking the differential of both sides. Doesn't really matter, but the basic concept is that you're taking the derivative and then you're moving the dx over. Because when we think about differentials, differentials are just variables. Dx is just a variable. So here du is a function of dx. So you can think of, up here you would say u is a function of x. Down here you would say du is a function of dx. So as your x change happens, then that's going to have some effect on the u change. So just think of the du's and the dx's, the differentials, just like variables. They can just move around, just like a variable would. So our next step would be to write this as e to the u. So there's our u, e to the u, and then we would, you don't have to formally do it, but you're essentially isolating the dx. If you can just look at this and see it, you don't have to write that third step. So the dx becomes du over negative 4. So we replace the dx with du over negative 4. And many people will just write it out in front right from the start. It really depends on what you feel comfortable with. If you're dividing by a constant, we know constants can just move in and out of integrals. They can move in and out of derivatives. So we can pull it to the front right away if we want. And then the integral of an exponential is itself. And then we do the back substitution. And we get to minus 1/4 e to the 3 minus 4x plus c. So this would be using the substitution technique. If you did RCR, you would go from here to there in one step, right? The integral of an exponential is itself. So you would just rewrite the exponential down. And then you would look in the exponent and say the derivative of the exponent is minus 4. We divide by minus 4, we'd be done. So we did 1, 2, 3, 4, 5, 6 extra steps. If you're doing RCR directly, you just do that. Divide by negative 4. So it is definitely the preferred method because it's quick and easy. All you have to do is recognize that this is linear, mx plus b. Okay, well, we already did that. So here are two other ones that you can do with substitution. And many times you have to use substitution. If the u is not linear, there's no RCR shortcut. So the RCR shortcut is just for linear substitutions. And that's why we focus on it a lot, because it's very frequent that your inside of the trig function or inside of the root is linear. So there's no need to go through substitution steps when it's linear. So here, if we do RCR, so we notice that this is linear, so we're going to go RCR. And the integral of the function, integral of cosine is sine of the same angle. So think about integrating the outside function and leaving the inside angle, leave it alone. So that, but then we do the reverse chain rule. So we're going to divide by 5. And you can write it as 1/5 or division by 5. Doesn't matter. You'll see both everywhere. Okay, you all try that second one with the root. That's one that we see probably, we see that a lot. And that was on the test. We saw it on the test, I think, in 2 places, where we had a linear radicand. If you have trouble when you see roots and things, rewriting it as a rational exponent could be helpful to you. You know, a lot of this calc stuff is putting things in a form that that's easier for you to identify. Like when you look at this square root notation, you might not want to call the inside of the root the base. But it is the base of this exponential expression here. Right? We've got this power on this quantity. We usually refer to that as the base. When it's in this form, it might not feel as natural to call it the base, and so it could be easier to goof it up. When you see the exponent here, for most people, it jumps out a little bit easier that, oh yeah, we're going to add 1 to the exponent. So when we add 1, we're going to get 3/2. Oops, we don't need the integration symbol anymore. We are integrating. So add 1 to the exponent, leave the base alone, divide by the new exponent. That gives us this 2/3 in front. And then what's the RCR piece? We're going to divide by 4, so we can put that wherever we want. Put a 1/4 right here, doesn't matter. And then a plus c for the integration constant. And so our simplification here would be 1/6 for x minus 1 to the 3/2 plus c. And if you want to do substitution, you could do that too. But I really want to get you not to do substitution when you can do RCR. Okay, any questions on either of those? This section is just a whole kind of collection of different types of individual techniques that we're going to look at. This one, they call it subtle substitution in the book. I have no idea why. I've never seen another book call it subtle substitution. No clue. The strategy is to get rid of negative exponents. That's what I would rather call this. Eliminate negative exponents, because that's the piece that's going to be problematic. So when we look at both these examples, we see that we have negative exponents. And in general, negative exponents are a pain anyway. And when they're in an integration problem, they're even worse. And so we want to get rid of them. So we use our classic math trick. We multiply by 1. That is how you can clear out negative exponents in one step. You can clear them out really quickly. Multiply by 1. Now, if you want, you could also say, let's move this into the denominator of this term. You could write it as 4 divided by e to the z. That's possible. Then you have e to the z in the denominator, and you want to clear out that fraction, so you're going to multiply through by e to the z. So here's what I recommend. When you look right there, we need to multiply that by something that's going to clear out that negative exponent. Here is what does that. We're going to multiply by 1. Multiplying by 1, standard stuff, because when you multiply by 1, you just change the look. You don't change the value. It's like a unit conversion. When you change from feet to miles, you multiply by 1. You don't change the value, you just change the units. You're just changing the way it looks. So I'm going to multiply top and bottom by e to the z, and that will clear out the negatives. Let's see. So in the numerator, e to the 2z times e to the z is e to the 3z. Add the exponents when you're multiplying. Down below, this quantity is going to need to be distributed. It has to go to here, and it has to go to there. So we have to distribute it across. The denominator has 2 terms, so that multiplication by e to the z has to go to both. So that's going to be e to the 3z minus what? 4. Because e to the z times e to the negative z, when you add the exponents, you get e to the 0, and e to the 0 is 1. So remember that basic fact. E to the z times e to the negative z is e to the 0, which is 1. Now, that is, for whatever reason, that's what they use this expression subtle substitution for. We haven't even done any substitution. So we have that. And maybe what they mean is that you have to do something before you can use substitution. Because right now, we can use substitution at this step. But we're actually a little more sophisticated. What form is this almost in? Log form. Yeah, good. What's the derivative of the denominator? E to the 3z times 3. So we can just make a little tweak. We can multiply by 1. We're so good at multiplying by 1. If we multiply by 1 like that, 3 times a third is 1. If we put a 3 in the numerator and then offset it by putting a 1/3 in front, we've just multiplied by 1. Now it's in log form perfectly. The denominator's derivative is identically the numerator. It's in log form now. So the integration is instantaneous. We know that it will be 1/3 natural log absolute value of the denominator. So there we go. Could you use substitution? Absolutely. What would you let u be if you were going to do substitution? The denominator. Because the denominator, one of the things we're going to notice that's problematic, if your numerator had 2 terms and your denominator had 1, you could distribute it, right? You could divide the denominator into the numerator. But when the denominator has 2 terms and the numerator only has 1, you're kind of out of luck. You can't break apart a fraction that has 2 terms in the denominator. Not yet. We'll learn some techniques. But we don't have a way, though, to manage when the denominator is 2 terms. We're trying to do something to combat that 2-term denominator. If it was in the numerator, we could just distribute the denominator. But that's not the case. OK, so that is in log form. There we go. And so when you're doing u substitution, you would let u be the whole denominator, and it will work out the same. OK, think to yourself about how you would eliminate the negative exponent in this one. So think, what can you multiply? So this multiplication by 1 is going to be hyper common. We are going to do this a ton starting today. Multiplying by 1. So think to yourself, what can I multiply by 1? What form of 1 should we multiply by in order to clear those fractions? Anyone want to guess?
Say this denominator but minus instead of plus.
Say that once again.
The denominator, but you're subtracting.
We don't want to multiply by the whole denominator, though, because then we'd have a FOIL situation, which is going to get more. We can multiply by 1 term. Top and bottom. What term do you think? Y cubed. Y cubed will be the one term that if we distribute it to the denominator, will clear out both those minuses all at once. Let's see how. So certainly in the numerator, we just have a y cubed. In the denominator, we have to do the sharing thing. Distribution. Y to the 3 times y to the minus 1 is y to the 2. And then y to the 3 times y to the negative 3 is 1. So that will be cleared out instantaneously. So we look to the highest negative power, and we want to multiply by the variable raised to the opposite of that negative power. So multiply by y to the 3. Okay, so now here, improper fractions. You maybe not have used that concept with rational functions. This is a rational function because it's got a polynomial below and a polynomial above. That makes it a rational function. So a rational function is when you have a quotient of polynomials. This is not what you wouldn't hear it. I don't think this is what they would call it in any book, really. But I think it's a good word to apply to this, and that is improper. It's improper. Like if you have 5 divided by 2, that is an improper fraction, right? Because the denominator is smaller than the numerator, so it's improper. When you hear the word fraction, most of us are thinking about a legitimate fraction, like 1/3 of something, or 2/3 of something, or 1/5 of something, like truly a fraction of a unit, a fraction of a whole. And if you write 5/3, yes, it's written as a fraction, but it doesn't really, it doesn't, it's more than 1. It's more than a unit. So 5/3 is bigger than 1. So we call that an improper fraction. It looks like a fraction, but it's not really a fraction of a whole. Same thing can be said for rational functions. This polynomial on top has a higher power than the denominator has. So we are going to think in that same way that, oh, that's an improper rational function because it's top heavy. The numerator's got more power than the denominator has. And we have a very special technique to deal with this called, what do you think, Skylar?
I've been sitting here for a few minutes and I can't remember.
Brandon, do you remember? So what we need to do, your favorite technique from algebra. Does anyone have an idea? If the new Bradley?
You multiply by the highest power in the denominator, like 1 over that?
Greatest common factor.
It's a reasonable guess. What if you see something like, if you have this, if you just have that, what are you going to do with the 25? You're going to divide it. So what kind of division is this called?
Long division.
Long division. Yes. Algebra techniques everywhere. So, but if you don't do that, you can try a whole bunch of other stuff, and you're just going to bang your head against the table. The key here is noticing that it's improper. And it's not something that is going to be easy because it's not something that you usually look at in calc. One, you certainly never talked about an improper rational function. You don't talk about it in pre-calc. But when it comes to integration, if this is improper, you're going to have to do long division. There are some that are improper that you might be able to do a clever multiplication and kind of bypass it. But most of the time, 90-something% of the time, you just have to do the long division.
Does synthetic division work too? Or is that
Well, when are you allowed to use synthetic division?
something with
If you know the intercept,
being linear?
Doesn't have to be.
You have to be dividing by something that's linear. You have to be dividing by y plus 1, y minus 2, whatever. The division has to be the divisor, the thing in the bottom, the denominator, has to be linear. That's the only time synthetic will work. So we can't use synthetic here. Synthetic is nice when you can use it because it's definitely quicker. So here we go, long division. So we're going to divide y squared plus 1 into y cubed. We say to ourselves, what times y squared will give us y cubed? Answer y. Y times y squared will give us y cubed. So we do this thing. And we're subtracting. And I will never distribute that minus just because if you make a mistake and you've distributed the minus, it's very difficult to go back and figure out where your error is. So I'll just put the minus out in front, put parentheses, and then do the subtraction. So this is y cubed minus y cubed, that's 0. And then up here, if you need to, you can put a placeholder. You have no y's up there, so you can put a 0y. So then we do the subtraction over here with this column. 0y minus y is negative y. 0y minus 1y is minus 1y. All right, and now we're done. As soon as the power on your term down here is smaller, not equal, it has to be smaller than that, then you're done. So now, just like you did in grade school, if you had something like 9/4, first you divide and you get the 2, and then you take the remainder and you put it over the divisor. We're doing the same thing here. So this is going to be rewritten as y minus y over y squared plus 1. So same process that we did with an improper fraction in grade school, same idea. And of course in grade school you have this shortcut that you wrote it like this, 2 1/4. But that really is 2 plus 1/4. Right? Now we're golden. What form is that fraction almost in
Log.
log form, right? So let's separate this before we do any integration. Let me just separate this. So integral symbols, just like derivatives, can distribute. So what we would do is write it like this first. So distribute the integral symbol. And then we say it's almost in log form. What form of 1 do we have to multiply by? 2 over 2. The denominator's derivative is 2y. The numerator just has a y in it, so we need a 2. We do it. We put a 2. But anytime we multiply the numerator by something, we must multiply the denominator by the same thing so that we're not changing the value. We're just changing the way it looks. Now it's in log form. So this will give us y squared over 2. This is going to be 1/2 natural log absolute value of the denominator plus c. Any part of that? Raise questions? Okay, so we have two different things happening here. So first off, we had negative exponents. We want to clear the negative exponents, so we multiply by the power of y to the opposite of the biggest negative exponent. That will clear the negative exponents when we distribute. Then we ended up with this improper fraction. Improper fraction, long division. Other techniques will usually give you problems. Now, when we get to trigonometric substitution, this particular one, we might have been able to do trig sub with. But it's a lot harder than this. Okay, let's go to this one. So here, we'll do one more and then we'll take our break. So here, this is kind of an example of what I was talking about a moment ago. The numerator has two terms. The numerator has a 3x and a 1 separated by a plus, so that's two terms. The denominator has a single square root. So you can think of that as one term, the square root. And we can split. This happens quite frequently where you need to split the fraction. So we are going to rewrite this as two separate integrations. Where we split the fractions. Okay, so that denominator gets distributed into each term in the numerator. Okay, the second one, we haven't, at this stage, this second one, we're just going to use the integration table. We're going to learn in the coming sections how to recognize it and how to do another technique that will give that to us. But at this stage, we're just going to recognize that this is an arcsine. All right, this one. What technique are we going to use here? Should be our number one technique. It's the only technique you really had before coming in today.
Multiply by conjugate.
So if there was not a square root, we might do a conjugate type things possible, but U sub. U sub is always our first technique. If you look at something, there's not an immediate antiderivative, U sub is something you should always consider. And U sub here is a good thing to consider because you always let U be the angle, the exponent, what's inside the root. But bless you. That's a quadratic inside the root. Its derivative is linear, and boom, you have a linear right up top. So that is a good candidate for U sub. If you have a quadratic that you let U be, then you have a linear up here. That's perfect. That's how we like it. So if we let U be 4 minus x squared, then du will be minus 2x dx. And so the natural thing here would be to isolate the x dx. And then you're hoping to replace, we want to replace that, there's x dx right there. We're going to replace that with du over negative 2. So let's keep trucking over this direction. So that 3 is in the way. It's not part of the derivative down here. So we're just going to factor that 3 out to the front. And then the x dx becomes du over negative 2. And the over negative 2 can come to the front. Dividing by a constant, that can always just be moved to the front. All right, so we're still focusing over here. And what is in the denominator now? Square root of u. And I'm going to move it to the numerator by making it u to the negative 1/2. Square root of u is u to the half in the bottom, in the denominator. And we know that the sign on an exponent is like a switch. Moves it up and down. It's like a little elevator. If you switch that to positive, boom, goes down. All right. And then plus this one, we're recognizing that it's in the inverse sine form. So this is, we can integrate this right away. This is going to be inverse sine of x over a. A in this case is 2. So we have that. Now we're ready to roll with the power rule. So we have negative 3/2. Add 1 to the exponent, divide by the new exponent. So we're going to get u to the 1/2. Dividing by 1/2 is the same as multiplying by 2. We've got that. Final step. Back substitute. So we've got our u expression here. We want to get back to the original letter. The original letter was an x, the original variable. So we have negative 3. We're going to put that inside the square root. If you don't want to write this, you could write this as a half if you want. Does not matter. And that would be our final answer. So, any questions on any of those? Any step there you're not 100% sure on? All right, let's go ahead and take our 10-minute break. And then we'll wrap up this section. And I'll let you all do the long division. The one thing I'm going to recommend is that you rewrite the numerator so that it's in descending order when you do this long division. So I would rewrite it as minus x to the 4th, and give yourself a little space. You might need a placeholder for a square or something in there. So I would set it up like that. And that should be a 6. So try that long division. Blow out the cobwebs. All right, so let's go through the long division piece. We'll deal with the integration in a moment, but just as a reminder for the long division, so we ask ourselves what times the x squared gives us negative x to the fourth. Negative x squared is that answer, so we distribute that across the divisor. So we're going to end up with, that should be a 4 right there and a square there. So we end up with that. That quantity is being subtracted from what's above, so make sure you subtract. You can change the signs if you want. It's harder to find your error, though, if you do it that way. So this part cancels. And then up here, if we want a placeholder of 0x squared, we have 0 minus minus, which will make plus. So we'll get 4x squared right here. Drop the 6. We're not done yet because the powers match. You're done when the power here is smaller, so not done yet. So we add a 4 here. Multiply across, we'll get 4x squared plus 16. And then we're subtracting again. So we think about this minus, put it out in front, wherever you want to put it. 4x squared minus 4x squared, of course, is 0. And then 6 minus 16. So that should be a remainder.
Wait, why did you need the plus 4 at the top?
To get rid of this.
Oh, okay.
Right, so when we do this subtraction, we have 4x squared. We want to get rid of that.
Mm-hmm.
So we have to ask ourselves what times this will match.
Oh, okay.
Any other questions up to that point? The thing on top is the quotient. So that comes first. That's going to be minus x squared plus 4. That's the quotient, just like over here. That's the 2 here. And then we add the remainder over the divisor. So minus 10 over x squared plus 4 dx. Question?
Where did the 16 come from?
This gets distributed across that whole thing. So it's 4 times x squared and 4 times 4. You see it?
Yeah.
Good. All right. So the first two terms, pretty easy. Power rule, so we'll have a minus x cubed over 3. We'll have a 4x. And then here, I'm going to do some stuff. We are going to see a lot of this form here. It's an inverse tangent. And we are going to approach the inverse trig functions in a slightly different way than those integration tables. And I'm going to start with this one. And what I want to do is this. So I know that the derivative of inverse tangent is 1 divided by 1 plus x squared. So that tells us that the integral of 1 over 1 plus x squared is inverse tangent. So the integral of 1 plus 1 over x squared, that's inverse tangent, plus c. And let me ask you a slightly modified question. What about if we had 1 over 1 plus 4x quantity squared? What technique of integration comes to mind? What was that? RCR. That quantity inside the square is linear. You could use substitution, say let's let u equal 4x, du equals whatever. But this is RCR here. This is linear, so that's RCR. So if we integrate this, we would get inverse tangent of whatever is inside the square there, but then we would divide by 4. Exactly. So that and this is my preference with all these inverses and things, when we get to the integration, if we can force it to have a 1 here, if we can force this leading 1, that's going to be a good strategy for us. And there's a lot of reasons that it's going to make things easier in the long run. Let me just go back for a second to this slide. Let me just point something out here. Let's see, it was actually the prior slide. So where was that inverse sine thing? Was it even further back? Inverse sine. Or did I miss it? Where was it? Didn't we have an inverse sine today?
Yeah, somewhere.
Somewhere we had an inverse sine. I know we did.
Question above the one we were just doing was an inverse sine.
Is it here?
Question 28.
28. And which one is this?
Oh,
There's inverse sine. Okay. So notice that the inverse sine one has an x over a here. With the inverses, if you look at the integration table, some of them have a 1 over a in front, some don't have a 1 over a in front when you're looking at the inverse ones. And so they're hard to remember. Let's go all the way to here because we can just look right there. So if you look at these, this one has no coefficient out in front for inverse sine. This one has a coefficient out in front. And then inverse secant also has a coefficient out in front. If you leave it in this form where you have a non-1 in those positions, then you have to memorize what goes out in front. My approach would be to minimize the least number of things possible to be successful. And so it's going to be easier for us, it will be easier for us if we can force there to be a 1 here and then use what we already know. If we can force there to be a 1 there, then we use RCR, then we don't have to memorize what goes out in front. It just comes out in the wash when you do the reverse chain rule, right?
If we didn't have a parentheses around that, we could not do the reverse chain rule, could we?
We could not. That's right. So if this was 1 plus 16x squared, that's not going to work. We have to have it wrapped up in parentheses first to use the
So
reverse chain rule.
On the test, we saw it around parentheses, then.
Yes. And if you had 1 plus 16x squared, you could make it have parentheses. Right? You could make the 16 4 squared. Yeah, which we'll see a lot. We'll see that quite a bit. So that is why the focus will be on this 1 for us. If we can force it to be a sum of squares with a 1, a leading 1, it's just going to be easier in the long run. There's going to be 3 less things to memorize. So that's what we'll do. So right here, when I look, I can factor this 10 out, no problem. That's in the numerator. But what about the denominator? There's not a 1 here. Right now, we have a 4. So if I want to make that a 1, what's going to get factored out? If I want to make that 4 a 1, can we just factor out the 4? So I'm factoring the 4 out of the 4, giving a 1. But there is no 4 here. And so what I'm going to do is think about it as 4 over 4. So the 4 that's getting factored out is this one. So what's left underneath the x squared? It's x squared over 4. And we just double check. If you take the 4 and you send it back across, if you distribute it, if you multiply it by this, you get back to the x squared. You multiply it by the 1, you get back to the 4. So factoring is going to be the key. And now, just like you pointed out, that's not inside parentheses yet. So we have one more step. And as you do this more and more, you would just do this all in one step. So here we would write this as x over 2 squared plus 1. Now we are in RCR form. Now we know it's an inverse tangent because it's the sum of squares in the denominator. If you look at them, the other two have differences of squares. For inverse sine and inverse secant, there's differences. For arctangent, sum of squares with a 1, perfect. Now we can just use the fact that we know it's an inverse tangent and we know that we have an RCR, we don't have to memorize whether there's a coefficient or not. It's just going to come out in the wash. So we're going to have 5 halves. This is going to be, I'm going to leave a little space for RCR. This is going to be inverse tangent of x over 2. And then what do we put in the RCR slot? A 2. We divide by half, which means multiply by 2. So this right here is RCR. Right? The derivative of x over 2 is 1/2. Everybody clear on that? Derivative of x over 2 is 1/2, so we divide by a half, which means multiply by 2. So derivative of this is a half. Dividing by half means multiply by 2. Okay, so there is our final answer. We can cancel out those. Any questions? Any step? All right. Another algebra technique, near and dear to your heart, completing the square. So we get to do long division today. We get to complete the square. We tried to do synthetic division. Okay, so complete the square. Right? Things you blocked out of your mind, now you have to let them back in. So completing the square, we look at this denominator, and the first thing that we should say to ourselves, can we use substitution? Is it in log form? Can we use substitution? And when we look, the derivative of the denominator is 2x plus 4, and that's definitely not the numerator. We can't just add a 4 in here. We can multiply by 2, but that's not going to create the derivative up there. So we can't do that. Substitution is not going to work. So complete the square. So here's what we're going to do. So we'll leave these limits the same. When you complete the square, you look at the coefficient of x. You look at the linear term. So we're going to look at the linear term. Anyone remember what we need to do? Divide by 2 and square. So that's how we complete the square. We divide by 2 and square. Because what we're doing is creating a perfect square trinomial. So let's divide by 2 and square. So we're going to have x squared plus 4x. We divide that by 2 and square, we get a 4. So we can add and subtract 4 if we want, or we could say, oh, we have an 8. Let's just break the 8. If we break the 8 apart, this is now a perfect square. So that's a perfect square trinomial. So it'll factor into x plus 2 quantity squared. So if we know we need a 4 to complete this square, we could borrow it from the 8, or you could add 4, subtract 4, and then combine the 8 with the minus 4, and you would get the same exact thing. So that is fine. How does it help us? Let's see. So the perfect square trinomial, this will be x plus 2 quantity squared plus 4 dx. Okay, starting to take shape. What do you think we should do next? Any? It'd be really nice in the denominator. So the denominator right now, we've got this extra x plus 2 in here. If we could make that like u to the 4th plus u squared plus 4, that would be a strategy. So if we just did u substitution right now, it's not quite in arctangent form, right? Because arctangent just has a 1 in the numerator. Right? We don't have an x. So we can't use arctangent yet, because that's not arctangent. So here's what we're going to do. We're going to be crafty and get rid of that x. We're going to say, let's let u be x plus 2. Then du is equal to dx. All right. So this is going to be, limits of integration are going to change. We're switching variables to u. And I don't think anyone's going to have trouble with this denominator. We're just going to write that as u squared plus 4. And du and dx are the same. But what about that x in the numerator? Right, we need to convert all the x's over to u's. We can't have x's and u's commingling. That's not right. So we have to get rid of the x. How can we get rid of the x?
U minus x.
Yeah.
Two.
Right? So up here, this equation right there allows you to go back and forth between u's and x's. You can exchange u's for x's or x's for u's based on this. So if we isolate the x, we would have u minus 2. Bingo. There's an x. That's what x is equal to, u minus 2. Okay. Limits of integration? 2 to, did you say 2 to 4? 2 to 4? So we plug x in here to get the corresponding u. Plug that x in there, get the corresponding u. Now, we have a numerator with 2 terms, so we can take that denominator and we can share it with the numerator. We can split the fraction. Whenever we have a numerator that's got more than one term, we can always take that denominator and share it with the numerator. So we are going to rewrite it. So let's not do anything except rewrite it like this. So we're going to rewrite it as u divided by u squared plus 4 du plus, or actually minus, I'm going to pull the 2 out to the front and just make it a 1 over u squared plus 4 du 2 to 4. So we split the fraction. So this denominator is getting divided into the u. That's this one. And this denominator is getting divided into the negative 2. That's this one. Negative 2 in the numerator can just come right out in front. What form is the first one in? Almost. Log. The derivative of u squared plus 4 is 2u. Put a 2 there. We better offset it. Now it's in log form. And the second one is an arctan. But so we could just use this and, and in the long run, we'd have to remember that we have to put a 1 over a out in front. Let's just do that right now, though. We'll learn next week, though, that we could just factor out the 4 and use reverse chain rule, like we just did a minute ago. Let's just use this one for now. Because the focus right now, I don't want to be on that. Let's focus on completing the square, splitting the fraction. There's enough to focus on. So this is 1/2 natural log. Absolute value of the denominator. We don't even need the absolute value, though, because u squared is always positive. U squared plus 4 is positive. So you don't have to put it. Doesn't hurt. You can do it, and it doesn't matter. So then this is going to go from 2 to 4. And then we're just going to use the identity, the trig table identity right there for now. So that's going to be 1 over a. So that's 1 over 2. So 1 over 2. Arctangent of x over a. So that's going to be arctan of u over 2. And then limits of integration are 2 to 4. All right, any question up to that moment before we do our evaluation? Yeah. Mm-hmm. So we're going to let u be x plus 2 so that the denominator looks like that, which should remind us of an inverse tangent. And then the problem is that when we let u be x plus 2, there's this leftover x. So we have to take that x and solve it for u to rewrite that x in terms of u. So if you're doing substitution, and your substitution takes care of everything except for part of it, then you can rewrite your substitution step to take care of the other piece that's left behind. All right, let's plug this in. So we're going to have 1/2 natural log of 4 squared is 16, so natural log of 20. And that's going to be minus, plug in the 2, that's going to be 4 plus 4 is 8. So I'm going to leave the, let's see, how am I going to do this? Let's put parentheses here. So the 1/2 is out in front, and so minus natural log of 8. Because we can combine those logs. Minus, these 2's are going to cancel each other out. So then we're going to have arctan of 2 minus arctan of 1. When we plug in the 2, we have arctan of 1, but we have minus a minus, so it's going to be plus arctan of 1. So this minus out here, just remember that there's a minus there. So when we do upper minus lower, this minus gets distributed, so we end up with minus upper plus lower. And what is arctan of 1? Pi over 4. This says what angle on the right half of the circle has a tangent value of 1. So the angle on the right with a tangent value of 1, another way to say that is the angle on the right where the terminal ray has slope of 1. And that's a pi over 4. So our final, we can make this 1/2 natural log. How do you combine subtraction with logs? Turn into division. So we can cancel a 4 out there, cancel a 4 out there, so we'll have natural log of 5/2, 20 over 8. Arctan of 2, can that be simplified? No. So that is our final answer. Okay. Last one on this slide. Do we have one more page of this still? Oh my gosh. Okay. So conjugate multiplication. Somebody mentioned conjugates earlier. And here is where they come up. So we've got this expression, and we know that with the trig functions, usually everything's squared. If we have things that are squared, we can use Pythagorean identities and make some changes. This is not a squared trig function, but we can make it a squared trig function if we multiply by its conjugate. So, whoops, if we multiply the bottom by that conjugate, we have to multiply the top by that conjugate. Once again, we're simply multiplying by 1. Multiplying by 1 is our trick. Okay, this gives us 1 plus cosecant in the numerator. And in the denominator, we have 1 minus cosecant squared of theta. That is an identity. What is that identity? Okay, if you can't remember right away, you can always go back. Let's go back to our primary Pythagorean, and we have that. There's our primary Pythagorean. And to get to the two alternate Pythagoreans, you just do division. What would we divide everything by to get to the cosecant identity? Divide by sine squared. So we're going to divide both sides by sine squared. Because on the right-hand side, when you divide by sine squared, you get cosecant squared. 1 over sine is cosecant. So this is going to give us 1 plus cotan squared is equal to cosecant squared. Now we just have to, massage it a little bit, pull the cosecants to the left, push the cotangents to the right. And what is this going to get replaced with? Negative cotangent squared. So we still have that in the numerator. this is going to be minus cotangent squared of theta d theta. So we've got that. Okay. This minus in the denominator, that will factor to the front. And then we are going to, so I'm going to factor that minus to the front. Then we're going to split fractions again. Whenever the numerator has two terms, you can always take the denominator and split it. So we're going to divide that cotan squared into each part of the numerator. 1 divided by cotan squared is tangent squared. Another thing we could do is change everything to sines and cosines. That's also a totally legitimate option. Which maybe that's even better, because here, this division here looks a little messy. Doesn't matter. So that minus is pulled out in front, so it's not there. So we have this. So we have, let's write it this way. So we have 1 over sine in the numerator. And if we divide by cotangent squared, that means multiply by the reciprocal. So the reciprocal is going to give us sine squared over cosine squared d theta. Getting there. Okay, so then let's just leave this tangent squared alone for a moment. So here we can cancel out one sine. We have that. Looking at the second one, this over here, what integration technique is going to do that for us? We have two functions in there. We have a sine and a cosine. Is there a technique that we could use that's going to work really easily there? What was that? Well, we just got rid of, if we just have sines and cosines, if we let u be cosine, then du is the numerator. If we let u be cosine, the derivative of cosine is minus sine, and then that's going to give us the numerator. So we'll have like a 1 over u squared situation. All right. Tangent squared. Do we have an antiderivative for tangent squared? Or do we have an antiderivative for secant squared? One of them has an antiderivative, one doesn't. Tan squared or secant squared? Which one has the antiderivative? Secant squared, because the derivative of what is secant squared? Tangent. So this one we can't integrate directly, but we know how to use that identity to come up with the tangent identity. The tangent identity says that tan squared is secant squared minus 1. That we can integrate. And then this we can integrate with u sub. So let's just split them apart. So we have that. And now we can, this one integrates pretty easily here. Oh, and I've got to be careful. This minus is way out in front. So either we put big brackets or we make that plus a minus. Yeah, let's do that. So we'll make that a minus, because this minus is out in front, so it's got to be shared. All right, let's put our u sub over here. We're going to let u be cosine. So then du is minus sine theta d theta. Integral of secant squared, tangent. Integral of -1, negative theta. This minus will distribute and make it positive theta. And this integral becomes, let's see, minus sine theta d theta, there's a minus, there's sine theta d theta, that all becomes du. So this is going to become u to the negative 2 du. All right, so the u is in the denominator. Cosine is u. U squared in the denominator is u to the minus 2 in the numerator. Almost there. So we have minus tangent theta plus theta. Integral of this, we add 1 and divide by the new exponent. So we get minus 1 over u plus c. And the only thing we have left to do is convert it back to theta. So 1 over u is 1 over cosine. So that's secant. And there we come up with an answer. That's a long one. You can see that it's going to be vital that you know your antiderivatives for the trig functions very well. Like when you get to this point here, if it's not pretty readily available in your mind that, oh, we don't have a function that has tan squared as its derivative, you can get very tangled up very fast. So make sure you have your derivatives. Brandon?
It's supposed to be plus 1 over u.
Let's see. So when we add 1 to this exponent, we get negative 1. And then we divide by that new exponent. So it should be negative.
Then we have the other, the 1 line up.
This one?
1 line up.
So notice this. It's minus sine. So all that becomes the du. You see it? So it's minus sine of theta d theta becomes plus du. So that minus we pull in there to take care of the differential. Okay. Long and crazy one. Two little weird miscellaneous ones. Integration, again, is you've got to be like a detective, and it's not trivial because it's not like a derivative. A derivative, you just do it. If it's a product rule, you use the product rule. If it's a quotient, use the quotient rule. If it's a power, use the power rule. Integration, all bets are off. So this one, we're going to let u be 1 plus root x. Then we're going to take the derivative so that we'll get a du equals 1 over 2 root x dx. So this is x to the 1/2, so its derivative is 1/2 x to the minus 1/2, which is that. 1/2 x to the minus 1/2. So over here we end up with, we're letting u be this whole thing in here, so that's going to be u to the 1/2. But then dx is du times, if we isolate the dx, we're going to have 2 root x times du. If we put that in here, then we have u's and x's. All right, so dx has an x and a u. That's not okay. So what do? So we solve this up here for root x. This tells us that root x is u minus 1, and that u minus 1 is going to go in right here. Now we have dx written with just u's. So that dx gets replaced with all of that. So we have 2 times u minus 1 times du. Limits of integration. When x is 0, u is 1. When x is 1, u is 2. So we use this to switch our limits of integration. And now we're golden. Now we are golden because we can factor the 2 out to the front. And in here, we end up with u to the 3/2 minus u to the 1/2 du. So u to the 1/2 times u to the 1, u to the 1/2 times -1. Power rule will work for both of those instantaneously. So this will be 2 times the quantity, u to the 5/2 times 2/5 minus u to the 3/2 times 2/3 from 1 to 2. Plugging in the 2, let's give ourselves a little space. So plugging in the 2, right there. The denominator makes it a square root of 2, so we have square root of 2 5 times. Square root of 2 twice is 2. So we're going to have 2 times 2, which is 4, square root of 2. So this is going to be 2/5 times 4 square root 2. Plug in the 2 here, square root of 2 3 times is 2 root 2. And then we subtract off antiderivative at 1. Okay, 1 to either of those powers is still 1. So we get that. And then we just have to get a common denominator, combine like terms, and get the simplified answer. So we can combine these, we can combine those, combine those. Let's not go through that arithmetic, but you could combine those. Any questions before that? Yeah.
Can you go over the u not being in terms of x?
Yes. So if we let u be this expression in x, so we take the derivative, we get that. The problem is that when you let 1 plus root x be u, you have a dx that you have to deal with. So then we come over here and we say, well, what's dx equal to? We multiply both sides by 2 root x. And we have that the dx is equal to this. And you can't have both x and u in the same integrand. You have to have one or the other. And so the trick is that we go back up to how u and x are related. And we see that we could solve for the square root of x. And we can rewrite the square root of x in terms of u. So that strategy works reasonably well when you can't have everything taken care of just by the regular substitution. If it doesn't work, you sometimes have to go back to your substitution step, and it feels a little bit, kind of, it feels a little funny, but it works. Because this tells us how u and x are related, and we have to make this all u's, so we have to turn that into u's, which is a little tricky. Okay, there's one more on here. Let's just set this one up. This gets at that mistake I saw a few times on the exam. You cannot split this square root. You cannot split square roots. Square roots are indivisible over a plus or a minus. So we can't split it. But that should look really familiar to you because just earlier today, we said that cosine squared of theta is 1 plus cosine of 2 theta over 2. So that's our power reduction identity. And when we look in here, we're like, oh, wait a minute. There's a 1 plus cosine right there. 1 plus cosine of 2x or 2 theta. So what we could do is multiply both sides over here by 2. And that is going to allow us to do the following. We can replace 1 plus cosine 2x with 2 cosine squared of x And we have that. And what is the square root of cosine squared? Cosine. Do you agree?
Yeah, just I don't like the answer.
So is the square root of cosine squared always cosine?
No.
No. Right? So you all should be very wary of this. That is not x. It's the absolute value of x. Right? That is not x. Unless somebody told you that x was positive. Right? If you have, let's just suppose x is -2, and you square it underneath the square root. This is the square root of 4. That symbol means the positive square root. So this and this are different. The square root of x squared is only x if x is positive. If x is negative, then the square root of x squared is negative x. Because this is inherently a piecewise defined function. This function means x if x is positive. It means minus x if x is negative. So we have to be a little bit careful. On this interval, 0 to pi over 2, is cosine positive or negative? Positive. If you're in quadrant 1, 0 to pi over 2, cosine is positive. So that's why we can do this. Because cosine is, in fact, positive on that interval that we're integrating on. So this is going to come up again. So if that's not 100% clear, don't worry yet. So this will be square root of 2. Sine of pi over 2 is 1. Sine of 0 is 0. So we'll get square root of 2. Is this ringing any bells? Hopefully. It'll come up again. Square root of a square is absolute value. And absolute value is a piecewise defined function. It'll come up again. Don't worry. All right, let's do a little bit start of integration by parts. So integration by parts is going to be your first really technical strategy for integration that's totally different from substitution. Everything we've done now is being very gimmicky. Let's split the fraction. Let's do this incestuous thing with the u sub where we plug back in. And there's all this sort of strategies that really are just a manipulation. Let's complete the square. Let's, very gimmicky. Integration by parts is going to be your second. U sub, of course, is a fundamental technique of integration. Integration by parts is our second major technique. It's not gimmicky. And integration by parts is basically what I would think of it as is a reverse product rule. That is a very good way to think about it. So this is a reverse product rule. You know the product rule for derivatives. And this kind of does that in reverse. Now, make sure in your mind when you say reverse product rule, you should see this as a quotient, but you should also see this as a product. Right? This is x times 1 over the square root of x plus 1. Or you can see this as a quotient or a product. Like if you have 5 halves, you can think of that as 5 times 1/2. So you can always think of a division also as a product. So with the integration by parts technique, we're thinking fractions and we're thinking proper products, but we're also thinking fractions. Those are products also. So we will talk about, we need to come up with a way to remember this formula right here. This is our integration by parts formula. And the strategy that I will use is by using this expression ultraviolet voodoo. Ultraviolet voodoo gives us a way to remember this thing on the right. UV is ultraviolet, and then we have a VDU, which we call voodoo. So ultraviolet voodoo. This is a very good way to remember that expression. Because there's U's and V's in here, DU's and DV's, and it can get very messy. But ultraviolet voodoo is a fantastic way to remember the right-hand side here. So what we do with integration by parts is identify a U and identify a DV, and then fill in the blanks. What do I mean by that? All right, here we go. So we're going to set up a little table. What we need to do is identify U and DV. So we want to take whatever this integrand is, and we want to split it into two pieces. We want to split it into U and DV. The dx has to be over here. It's got to be over there. We can't have the dx with the u. So we have to split this apart. And let me just put a couple of lines here. So once we have our u and our dv, what we are going to do is take the derivative of the u column and the integral of the dv column so that we have all four of these things which we can then fill in the blanks up here. So we need four quantities here. We'll set it up the same way every time. The top row is going to be u dv. So we have to look at our integrand and we have to break it apart. We have to choose what's going to be u, what's going to be dv. Sometimes there's multiple choices that will work. Sometimes there's only one thing that works. Rule of thumb number one. When we put stuff for the u and the dv, notice that to get to v from dv, we have to integrate. So we want to be careful and make sure that whatever we put here is easily integrable. And over here, to get to du from u, we have to differentiate. So we want something that's easily differentiable. Integrating is harder than differentiating. So that's where I would focus first. It's like, okay, we have really two choices here. We have an x, and we have a square root of x plus 1. Okay, so we can, here's one choice. We could do this. That's one choice. Or we could put that here and the x there. Those are two choices. It's impossible to know ahead of time which one's going to work. Maybe they both work. Maybe one doesn't work at all because you end up with something that's not integrable.
Could you not do like what you do with the substitution and only do the x plus 1?
No. So we can't break apart the square root here. If we were doing u sub, that's what we would do. Yeah. But here we can't. The square root has to stick with the x plus 1. So another rule of thumb is that when you're differentiating, if you can reduce the power, that's a helpful thing. So if you put a power of x here, when you differentiate, the power is going to go down. So let's just try this setup and see if we get anywhere. So we take the derivative of x, that's just 1. So we get 1 dx. Now we have to integrate this thing over here, so let's come off to the side. We're going to integrate, and it's always easier to write it with a negative exponent. Let's see what happens here. So we're integrating that, so we just use the power rule. So this will be x plus 1 to the positive half, dividing by positive 1/2. And another cool thing about integration by parts is you can always choose your constant of integration to be 0. We don't have to worry about the c.
Isn't that a true function though? Couldn't you like the inverse of the derivative of the inverse of something? Isn't that?
Not without the square. So all of the trig ones are going to have a square built in. So this one, that's going to be our integral. Let's see what happens. So this is going to be 2. If we want to write it as a root or a 1/2, doesn't matter. So there's v. All right. So now this is sort of like a roadmap here. This is our recipe. Now the right-hand side is our ultraviolet voodoo. So now we have our integral. right there. So this is going to be equal to uv. So uv is this main diagonal, uv. So that's going to be x multiplied by 2 multiplied by square root of x plus 1. So that's uv. Ultraviolet minus the integral of v du. V du is the bottom row. So it's always going to be main diagonal minus the bottom row. So v du, this is our voodoo part. So there's v, du is dx. So we're going to have this right there. So that is uv minus integral of v du. And here is the key. It's at this stage right here, make that all black. So it's at this stage right here where we have our next integral. And here's where we ask ourselves, did we make the right choice for u and dv? We know we made the right choice if that integral is integrable. If you come down here to something that's worse than what you started with, then you chose the wrong u and the wrong dv. So this is where we make that decision. And ahead of time is very, very difficult to know. So you pick your u, you pick your dv, right there. Now we assess that is integrable, so we made a good choice. So we just go ahead and integrate that. So once again, we can just use the power rule. So we have 2 times x plus 1 to what power now when we use the power rule? 3 halves. Divide by 3 halves, and then add c. And so all we can do is combine these, make this 4/3. And so that was the right choice, because we got down to another integral that we could integrate. All right, we'll stop there, I think. Yeah, we'll stop there. And look at this integration by parts. We've just done one problem. Look in your online textbook or your whatever, if you have a hardback. Look at integration by parts. Look at some examples, because it can feel very unsettling. And you want to look at a few examples before we do a bunch more on Thursday. We'll do a ton of examples on Thursday, but do some practice. Question? Yes. Done. Yeah, let me, I'll rewrite it so that it's in simplified form. Yeah, so the only thing we can do is combine that 2 and the 2/3. So yeah, this is our final answer. Final answer right here. So up here, when you do this integration, you can always choose c to be 0. If you want to pick something else, but that's pick 0. Yeah, if you pick 0, it's always going to work.
None of those have the videos, but I'm not learning.
Pause on.